Thank you all for joining us today. I'm very pleased to introduce Laura Wallace from GNS Science for the International Webinar Series of SZ4D. This International Webinar Series has been going on since last spring, and we've been taking a bit of a tour of global thinking about subduction zone geohazards. It will continue. We will be having, you can take a look at SZ4D.org for upcoming webinars. We will be going shortly to the Western Pacific. Well, we are today, and we will continue in the Western Pacific. Some of the, we will be shifting later in the spring to a Thursday afternoon time slot to enable some speakers from Taiwan and Singapore to join us more easily, and also audience members from the Western Pacific. So keep your eye on your email at SZ4D.org to keep apprised of those seminars. Another announcement is that obviously this seminar series is part of the SZ4D research initiative, and which has been chugging along on trying to formulate a plan for science implementation of the SZ4D vision of improving our understanding of geohazards in subduction zones. And to that end, there will be a town hall on February 26th from 11 a.m. to 1 p.m. Pacific time. Again, the registration for that is open. That will involve short presentations from the working groups of SZ4D and much longer discussions via breakout rooms to try to solicit input. So please mark your calendars and join us for that event. Okay, so now we're on to the main event, which is Laura Wallace from GNS Science in New Zealand is going to talk to us about the Hikurangi Subduction Zone. Dr. Wallace is quite eminent in this field and others. She is a member of the Royal Academy of New Zealand, Te Arapo. Please help me with my Maori pronunciation.
The Royal Society of New Zealand.
The Royal Society of New Zealand. And she is also was a major organizer and chief scientist of the Hikurangi expedition that she's going to talk to us about shortly, and a major contributor to our understanding of slow slip and when and where geologically and geophysically it happens. I think she's also somewhat uniquely positioned to comment on the intersection between policy and public safety and these somewhat esoteric otherwise observations of slow slip and subduction zones. And so I hope she might address some of that perhaps in questions at the end. Thank you very much, Laura, and I look forward to your presentation.
Great, thanks, Emily. Thanks for inviting me. So I'm going to take you guys on a tour of the Hikurangi Subduction Zone because there's been a lot going on here in the last 10 years. And let's see, there we go. So just before I launch into this, there's a ton of people involved in the stuff that I'm going to be talking about for the next hour. And these are just a few of those people. There's lots more. And I just want to acknowledge those folks. And some of these people have also given me some slides and material to show today. For the Hikurangi Subduction Zone, if you're not familiar with the Hikurangi Subduction Zone, it's located offshore the east coast of New Zealand. Off the east coast of the North Island. It's really it starts somewhere in the northern part of the South Island, and then it continues northward and connects up with the Kermadec and Tonga Trench further north. So it's really collinear with those trenches. At this subduction zone, we have westward subduction of the Pacific Plate beneath the eastern part of the North Island along the Hikurangi Trough. The two plates, the Pacific Plate and the Australian Plate, are converging through this region at about 4.5 centimeters per year, roughly. However, that plate motion is oblique. This white vector here, you can see this angle, it's at an oblique angle to the boundary, but the slip in this region is partitioned in that the margin normal component of this vector is accommodated along the shallow megathrust, while the margin parallel component of that plate motion vector is accommodated in the North Island dextral fault belt. This is a system of strike slip faults, and also via a clockwise rotation of the eastern part of the North Island. The eastern North Island is basically rotating it as its own microplate independent of the Australian plate. And this results in rifting in the central part of the North Island, or it's actually intra-arc rifting in the topovolcanic zone in here. And then as that microplate swings back in, we have a lot of transpressional deformation in the upper plate. This rotation of the eastern North Island also results in some big changes in convergence rate at the trench along the subduction zone. In the southern part of the Hikurangi margin, the convergence rate at the trench is about 2 centimeters per year. And this increases threefold to the north to about 6 centimeters per year. One of the interesting and I think very fortuitous characteristics of this subduction zone is that the type of plate being subducted beneath the North Island, it's not normal oceanic crust. It's actually a Cretaceous oceanic plateau, a large igneous province, the Hikurangi Plateau. And because it's slightly over thickened relative to normal oceanic crust, as it's being stuffed under the rug, it serves to really jack up large portions of the forearc of the subduction margin. So we have a lot of our overlying plate actually exposed above sea level in New Zealand compared to a lot of other subduction zones. And this sets up a situation where we can use a lot of land-based methods like continuously operating GPS, onshore seismic networks, and so forth to monitor things that are happening on the subduction interface at a broad range of depth levels on the interface. And just for context, the plate interface, where the subduction plate boundary occurs beneath the east coast of the North Island at about 12 kilometers depth. And for context, for many other subduction zones like Cascadia and those in Japan and other places, that equivalent shallow part of the plate interface can be, 50 to 100 kilometers offshore. So it's much more difficult in a lot of other places to investigate processes happening on the shallow interface. You really have to turn to marine methods in a lot of other places. Although, as I'm going to show in the talk, we've been making, a large number of people have been making a big foray into better understanding the offshore part of the margin as well. And I'm going to highlight a bunch of those studies later on today. And then some other things I want to highlight about this margin that's really important are some of the other along strike changes that we observe, particularly in the characteristics of the offshore subduction margin. You can see these dashed contours that are numbered. These are showing the thickness of the sediment on the overlying overlying the Hikurangi Plateau in kilometers. And so in the south, you can see we've got about 3 to 5 kilometers thickness of sediment entering the subduction margin here in the south, whereas in the north, the sediment thicknesses are generally a kilometer or less. This also coincides with a big change in the morphology and the nature of the offshore accretionary wedge and the overlying plate. So in the south, we have this really broad, well-developed, really kind of classic accretionary wedge with a low taper angle. And this is in the area where you've got thicker sediment coming in. Whereas in the north, we have a very narrow, active outer wedge. It has a fairly steep taper angle. And in a lot of cases, you might almost consider the northern part of the margin as almost being the kind of a subduction erosion type end member. The other thing I wanted to point out is the sediment thicknesses. This has a big influence on the roughness of the incoming plate. So you can see in the north, we've got all these seamounts protruding above that thinner sedimentary cover, and that's probably influencing that wedge morphology and evolution in the north, when we have all these seamounts coming in, whereas in the south, any seamounts on the Hikurangi Plateau are largely blanketed by that very thick sediment cover. So one of the other important along strike variations in megathrust slip behavior that we've been able to resolve largely from geodetic studies, both with campaign GPS and also continuously operating GPS, I guess I should say GNSS, that's what we're calling it now. Hard to teach an old dog new tricks. But some really big changes in the degree of interseismic coupling and also the distribution and occurrence of slow slip events. I'm sure you guys have been hearing about slow slip events. throughout this series, so I'm not going to explain what those are, but there's essentially earthquakes in slow motion that take weeks to months, to years to occur. In terms of the interseismic coupling, this map here showing the blue to red colors, the red areas are where the campaign GPS measurements are suggesting a lot of contraction and elastic strain accumulation in the overlying plate. And this red is a distribution of high interseismic coupling that we obtained from the campaign GPS data. So we have this deeply coupled area in the south that's coupled down to about 30 kilometers or so, where we have a lot of locking and elastic strain accumulation. And the north, you can see this blue areas where the interface, at least right now, appears to be mostly creeping. And we have this sharp transition through the central part of the North Island here. So we have a really nicely resolved transition from a deeply locked megathrust, where we expect, potentially magnitude 8 or larger earthquakes, to an area which is currently undergoing mostly aseismic creep. Then if we also look at the distribution of slow slip events in relationship to this, these red contours are the cumulative slow slip. In our shallow slow slip area here in the north, we have this is from 2002 to 2014, just this figure. And most of the slow slip in the northern part of the margin is occurring offshore the East Coast. So it's sort of less than 10 to 15 kilometers depth. Whereas we go to the south in the area of deep locking, we have deep slow slip events occurring, really kind of following that down dip limit of interseismic coupling that we observe in the south. And so this is sort of typical, having these deep slow slip events following along that transition from interseismic locking to aseismic creep deeper down is typical of a lot of other subduction zones where we have deep slow slip events as well. They seem to be occupying that transition at the bottom end of the seismogenic zone. The slow slip events in these two areas have very different characteristics. In the north, the slow slip events, the shallow ones, they tend to be fairly short, lasting a few weeks. And they tend to happen fairly frequently in most of those areas, about every 1 to 2 years. Whereas in the south, these are less frequent. They occur about every 5 years, and they're also quite long-term, long-lived slow slip events lasting about a year. More similar to the types of slow slip events that are observed in the Bungo Channel in Southwest Japan and also the Guerrero region in Mexico. In both cases, however, these slow slip events are quite large. In terms of the surface displacements at the GNSS sites on the surface, you often get 3 to 4 centimeters of horizontal and vertical displacement in these events. So they're quite large events. Sort of in comparison to, say, Cascadia, some of the events are, in New Zealand are about 10 times larger than the ones in Cascadia. So they're pretty easy to see, at least in the onshore part with the continuous GNSS network. So this diversity of slip processes that we observe here with this really deeply locked subduction interface in the south with deep slow slip events to this mostly creeping interface in the north, with these very shallow slow slip events, has really made this an ideal location to investigate the processes that underlie megathrust slip behavior. And there's been a number of large experiments that have been undertaken in the last several years that have really set out to try and resolve, what are the physical processes that are controlling these along strike variations in megathrust slip behavior, and I think that getting at that, may help us to understand that problem globally as well. What are the characteristics that cause some subduction megathrusts to lock up and slip in big earthquakes, while others may creep or produce more moderate magnitude earthquakes or shallow slow slip, for example. And then the shallow slow slip that we have off the East Coast, as seafloor geodetic studies that I'll show later suggest that these go potentially almost all the way to the trench. So the fact that they're so shallow provides some really exciting opportunities to look at to really image the slow slip area and also monitor the slow slip event processes in the very near field, to within kilometers of the source, and also to undertake scientific ocean drilling. And all of those efforts have been underway. I'll talk about many of these in the rest of this talk, but we've had a IODP drilling effort on a transect across the shallow slow slip area a couple of years ago There have been a couple of really neat seismic experiments, a New Zealand 3D experiment led by Nathan Banks and Greg Moore and Harold Tobin and Eli Silver and others to do really high resolution imaging of the shallow slow slip area in the north. There were also OBSs deployed. So Jamstack has been really key player in this with deploying OBSs during these active source experiments, and that's going to allow for some more really interesting imaging opportunities. And then the Shire experiment, which was also an active source experiment that collected a series of lines, some of which OBS were deployed along during the active source shooting to really look at imaging more broadly the changes in characteristics along the margin. And I'll talk as well about some controlled source electromagnetic experiments to get at the offshore conductivity structure and a variety of other rolling seafloor geodetic and OBS experiments and so forth. Something I want to point out, these efforts have really depended very heavily on very strong international collaboration between New Zealand, the US, Japan, the UK, and Europe, and have really benefited greatly from IUDP drilling initiatives, the selection of New Zealand as a geoprisms focus site, also the GeoNet network. I'm showing some of the GeoNet sites on shore here, the seismic and continuous GNSS network, and also access to both New Zealand and US marine research vessels. For example, the seismic experiments I mentioned involved, for example, the Langseth to do the active source work, and then the New Zealand research vessel Tangaroa was handling the OBS deployments and recoveries. So a great example of international cooperation and what you can do with that. Okay, so I'm going to talk for the first part of the talk about some new insights that we've gotten over the last several years into processes behind these episodic slow slip events. So I'll start out with one of the most surprising observations since we've been monitoring slow slip events was actually following the 2016 magnitude 7.8 Kaikoura earthquake. That was down here. Many of you, I'm sure, have heard of that earthquake. You can kind of see the green lines showing some of the surface faults that ruptured. That occurred in the northeastern part of the South Island, really at the far end of the southern part of the Hikurangi Subduction zone. Immediately following that earthquake, there was widespread triggering of slow slip in most of our slow slip areas on the Hikurangi Subduction zone. I want to focus quite a bit on this East Coast triggered slow slip, which was really immediate. The triggering initiated up here in the northern part of the subduction zone and propagated to the south over a couple of weeks. And the initiation of this triggered event off the East Coast was actually about 600 kilometers away from the Kaikoura earthquake. So that really suggests that the more likely triggering source of triggering was related to the dynamic stress changes occurring on the plate interface as those seismic waves from the Kaikoura earthquake propagated through the region. Another really interesting finding from that is if you look at the seismograms from the sites along the East Coast here. So in the south, these are the ones near the Kaikoura epicenter. You had about 150-second duration of ground motion. However, as you get up into this area, which these are sites up in this Gisborne region, the ground motions increased dramatically to about 450 seconds. I think these are some of the longest duration ground motions ever observed from a similar magnitude earthquake. So something was going on that we think actually played a big role in this dynamic triggering of slow slip up here. In order to fit this increased ground motion duration, Yoshi Kaneko did some modeling, and he's had a paper a couple of years ago if you want to find out more about this. And really the only way you could fit that data was to put a very low velocity wedge above that area where the slow slip, triggered slow slip initiated, a VS of less than about 1.5 kilometers per second. And he was able to reproduce that long duration ground motion. So we think there was essentially a basin effect from this really low velocity outer wedge that really served to both amplify and increase the duration of dynamic stressing from the passing seismic waves, leading to the triggering of slow slip there. So I think this is kind of important to think about other margins, in areas where you may have a very low velocity wedge. Those areas may be more susceptible to dynamic triggering from more distant earthquakes. And then one of the other things we've been doing, although the continuous GPS network on shore has been fantastic for resolving slow slip processes in New Zealand, for these offshore events, we're really limited in what we can say about the distribution of the events and also the trenchward extent of these events. So in 2014, we undertook the Hobbits experiment, which was a deployment of 24 seafloor pressure sensors and also 15 ocean bottom seismometers. And the purpose of the seafloor pressure sensors was actually to do seafloor geodesy. So the seafloor pressure sensors, they're essentially continuously measuring absolute pressure at the seafloor for the duration of the deployment. And this can be useful for actually getting at vertical deformation of the seafloor during these slow slip events. Because as you can imagine, if the seafloor goes up during a slow slip event, you have less water above you, you're going to record a pressure decrease. So this is just showing the time series of the seafloor pressure changes after some corrections for the tides and oceanographic effects, and also instrument drift effects. And the upshot is that for the sites above the slow slip source out here, we recorded seafloor pressure decreases equivalent to about 1 to 5 centimeters of uplift above the slow slip source. This slip distribution that we get in this particular model, we've published a few other models since then with people doing different things with the slip inversions. We're getting about 20 centimeters of slip on the plate boundary at about 6 kilometers depth. And this continues probably to within at least 2 kilometers of the seafloor. It's possible that the slip went all the way to the trench. We can't tell that for sure based on the distribution of our sites. But again, this was another one of these internationally collaborative projects involving particularly the US, Japan, and New Zealand. And it was a lot of NSF funding and also funding from New Zealand and Japan. Okay, the Hobbits experiment also included OBS, and this has helped to reveal the tremor and the microseismicity in the slow slip region and occurring during the slow slip events as well. On the left, this is a figure from a paper by Phil Barnes, but the thing I want you to zoom in on is the yellow dots, which are tremor locations from some work that Erin Todd did. She was a student at UC Santa Cruz, and she sees these 2 clusters of tremor during the 2014 slow slip event, up here in the north, and then also one down here near the trench. In both cases, these tremor locations, they're located down dip of subducting seamounts. So up in the north, this white contour is showing the location of a subducting seamount imaged from magnetic anomalies and also seismic reflection imaging. And you can see that tremors clustering down dip of it. And likewise down here, this seamount Puke Knoll, which is coming in, we've got tremor occurring down dip of that. So there's some interesting relationships with subducting seamounts and the locations of tremor. On the right, this is just showing a catalog of seismicity developed by Jefferson Yarse through the Hobbits deployment, and was able to see that really literally thousands more earthquakes than is possible to observe with the onshore seismic GeoNet seismic network. So the OBS really do make a huge difference. The microseismicity in this area is located dominantly in the subducting plate, but there's also some near the interface and in the upper plate. And then on the right, these are just some earthquake focal mechanisms developed by Emily Warren Smith from the Hobbit seismic data. So Emily was actually able to do some really interesting things with those focal mechanisms and looking at changes in the stress tensor during the slow slip cycle in the during the 2014 slow slip event from the Hobbits experiment data. One of the things that she noted was in the lead up to the slow slip event and prior to the slow slip event, there was a lot more strike slip faulting accompanying the normal faulting in the top of the subducted slab. And then during the slow slip event and sort of just following it, immediately following it, there was more normal faulting during the slow slip event. So she was able to, she has made the interpretation that this is potentially related to changes in fluid pressure in the top of the slab beneath the sort of impermeable fault zone. Basically, between the slow slip events, you have fluids accumulating at the top of the slab beneath the fault zone there. And then potentially those fluid pressures drive up and cause, serve to essentially trigger the slow slip event. Then that impermeable seal breaks, those fluids bleed off. And that's why when you have the normal faulting, dominantly normal faulting going on, and then, once the slow slip event finishes, the process starts all over again. So this is some really interesting observations that fluid cycling may actually be modulating the slow slip timing. This is essentially similar to the kind of fault valve behavior that people like Rick Simpson have been talking about for a long time. We didn't stop with the Hobbits experiment in 2014. We've been doing rolling seafloor geodetic experiments since then. We even have some instruments out right now. This is some data from one of the larger slow slip events that we've seen in the last few years. We had seafloor geodetic, we have absolute pressure gauges and ocean bottom seismometers out off the East Coast during a really large slow slip event in 2019 that extended from north of Gisborne down through offshore Hawke's Bay. We had a few sensors in the Hobbits deployment area, which was right this northern part here. And then we also had some sensors offshore Hawke's Bay, which we had never done any seafloor geodetic or OBS deployments out there before. And this is showing the top time series, and the bottom time series is showing seafloor pressure changes recorded during this slow slip event. This is from some work that our PhD student, Catherine Woods at Victoria University is doing. In the Hobbits deployment areas, the seafloor pressure sensors recorded about 1 to 2 centimeters of uplift during the slow slip event. And then down in the Hawke's Bay area, the 2 northern sensors and this other one near the trench recorded about 1 to 3 centimeters of uplift of the seafloor. And that was just following where the main deformation occurred in the continuous GPS time series, suggesting potentially that the slow slip migrated up dip towards the trench. These two P1 and P2 didn't see any appreciable seafloor pressure changes, suggesting this is really at the southern edge of the slow slip event in that area, which is also consistent with the onshore GPS data. So just to look at, this is from a slip model that Katie's done from that event. This is the total slip in the 2019 event. And I just want to relate this to the source area of past subduction earthquakes. These 2 stars up here at the top, these are the location of 2 earthquakes in 1947. They were about a magnitude 7, and they're very unusual as they caused quite large tsunami at the coast, about 8 to 10 meters along the coast near Gisborne. And this is pretty large given the relatively modest magnitude of those events. And these are probably, what we call tsunami earthquakes, which, earthquakes that produce much larger tsunami than expected from the magnitude. And so the source area of these overlap very, significantly with the source area of shallow slow slip off Gisborne. And then also this red ellipse down here, this is showing an approximate rupture region of subduction earthquakes inferred from paleoseismological studies that have been done along the Hawke's Bay coastline. They've basically been coring in that area and see these alternating peat and estuary and clay layers, and also in some cases tsunami deposits. And if those are related to subduction earthquakes, the source area of that would be out here. And this also overlaps significantly with the shallow slow slip off Hawke's Bay. So I think this is a really important thing to keep in mind, because I think, based on these things, it's very likely that these shallow slow slip event source regions also can host, seismic rupture that may pose sort of pretty large, particularly tsunami hazard and also seismic hazard. And I think a lot of us tend to want to think that the slow slip regions are not going to be significant players in the production of earthquakes, but I think this example shows that that's not necessarily a safe assumption, and we need to be considering this. Okay, so our latest current deployment, where we have instruments out right now in terms of absolute seafloor pressure sensors and OBS, is off the central part of the Hikurangi margin. You can see this red box here. This is a little further south than we've ever had these types of deployments before, so it's going to be pretty interesting to see what we find. But we're targeting a shallow slow slip event that occurs in this area, basically in the transition from the deeply locked area to the creeping area in the north. And this slow slip event, at least since we've had continuous GPS, has been occurring almost like clockwork about every 5 years. And so we're really targeting that next event with this deployment. We're also going to have an onshore, this is going to be an amphibious experiment. We're going to deploy 50 broadband seismometers and some temporary GPS as well in a couple of months, and probably leave those out for about 1.5 years. So this event is of a lot of interest, because this particular slow slip event, more than any of the others along the Hikurangi margin, is intensely associated with a lot of microseismicity when the events occur. This is just showing past events and earthquakes that have occurred during the events including up to a magnitude 6.1 in the 2016 event. We saw a magnitude 6.1 thrust event out, not far from the trench here. So this is a great opportunity to look at the relationship between slow slip events and seismicity. And we also want to further test some of these ideas of Emily Warren Smith's about the role of fluid cycling and the timing and occurrence of slow slip events. And this project is involving a collaboration between New Zealand and Japan. Okay, and just to give you one last sort of bit of some of the seafloor geodetic related measurements that we're doing and infrastructure that we've installed. We had I mentioned the IODP drilling expeditions earlier. We had 2 IODP expeditions in 2018, late 2017, early 2018, targeting a transect of sites across the plate boundary here. This is again, that Hobbits experiment area at the northern margin. The black contours were the 2014 slow slip event. And during this expedition, one of the things that we did was we installed 2 observatories, which are out there operating right now. One of these observatories was right out near the deformation front and penetrating a very active splay fault near the deformation front, the Papaku Fault. And then another observatory further landward above that really high slow slip patch. The fault zone observatory is probably the most complex one that we installed, and that involves 3 levels of pore pressure sensing in the hanging wall, the fault zone, and the footwall. Also a string of temperature sensors, and also these things we call osmoflowmeters and osmosamplers, which are basically measuring rates of fluid flow and also doing time series sampling of fluid. So we can ultimately, when we recover that string, look at potential changes in the geochemistry of the fluids flowing through the fault during the slow slip cycle. The pore pressure is, from a seafloor geodetic point of view, is probably the thing that interests me the most, because you can use pore pressure essentially as a proxy for volumetric strain. So depending on where the slow slip event is relative to the observatory, if you undergo contraction during the event, you'll observe a pore pressure increase. If you undergo extension, you'll observe a pore pressure decrease. And so these pore pressure measurements are really going to help reveal this sort of detailed spatio-temporal evolution of these shallow slow slip events, really close to the source. And it's always possible slow slip travels up this splay fault as well. So that'll be another interesting thing to potentially look at. And I'll also note the 2 observatories straddle this subducted seamount here. So we'll be able to look at the relationship between the slow slip evolution and the seamount and any influence the seamount might have on the slow slip propagation. Okay, we did actually go and do our first visit to these observatories to download the first round of pressure data in February of 2019 with the ROV Jason. This was about 10 months after they were installed. There was a very tiny slow slip event to the south. There weren't any major slow slip events between when we installed them and when and 10 months later when we went to retrieve the data. But we are getting back out there in a couple of weeks now with the ROV Ropos on New Zealand's vessel Tangaroa, and we're going to go do a download of the data, and that's when we'll be able to download the data recorded during that really large 2019 slow slip event. And there's been a few other smaller events that will be recorded on the pressure sensors as well since then. One of the other things we're doing with the ROV is we're going to be recovering some seafloor flow meters that Evan Solomon from University of Washington deployed a couple of years ago as part of the Safran's project. This is a picture of one down here on the lower left. He's got quite a few of these above that large slow slip event in 2019 that we're recording during that time. And so this is going to be a really interesting opportunity to see if there's any change in the flow rate of fluids out of the seafloor during this slow slip event. So just point out, we've had a really, for the 2019 event, a diverse array of instruments out there, OBS, seafloor pressure, the downhole observatories, the seafloor flow meters recording during that event. So this is going to be a pretty amazing opportunity once we get all this data to look at the interplay between slow slip event occurrence, the seismicity, and also the hydrogeology. Okay, so I want to get a little bit into the sort of structure and the sort of physical properties of what's going on in these shallow slow slip event source. I pointed out earlier, we've got these seamounts protruding above the sort of thinner sedimentary cover on the incoming plate. So you probably have quite a lot of geometric heterogeneity of the plate boundary and a lot of roughness. Mentioned also this seamount that's been imaged, that's been subducted here, that's involved in the slow slip area. Yeah, so there's probably some significant influence from this geometric heterogeneity. And, it's possible as these seamounts are plowing in and peeling off parts of the outer wedge, that you also may have a more melange-like plate interface as well. I'm going to talk in the next slide about some ground truthing of what's actually going into the slow slip area, and some smaller scales of heterogeneity there from the IODP drilling. But another thing I want to point out before I leave this slide is this really large slip patch back here, this sort of 20 to 20 centimeters or so slip in the 2014 Hobbits event back here, corresponds on this to this part of the seismic reflection line. This is a seismic line running along this black line here through the IODP drilling transect. There's this high amplitude reflectivity zone back here, and that's been interpreted by Rebecca Bell and others as being possibly subducted underplated sediments, possibly fluid rich. So if that interpretation is correct, then there's probably also a lot of involvement potentially in terms of high fluid pressure and the occurrence of slow slip events, which has been suggested by a lot of other studies as well elsewhere. Okay, so just looking at some of the IUDP drilling results and the implications of this for what might be caught up in that slow slip zone. This is from a paper that Phil Barnes led last year. And this is really focusing on, I'll go back here, on these two sites on the incoming plate. And these sites are really important in the IODP aims, because these two sites are sampling the sedimentary section and the top of the Hikurangi Plateau where the décollement is forming. And so we were actually targeting what are basically the slow slip event protolith rocks right before they're being subducted and being caught up in that slow slip area, because that's really our best chance to get at what are the kinds of materials involved in slow slip. So you can see from Phil's interpretation of the seismic, the décollement's largely forming in the sedimentary sequence on the top of the Hikurangi Plateau. And so that was one of our major targets for the IODP drilling in terms of logging and coring. And so you can see, if you tie this back to the site U1520, it's this blue shaded area that's really of interest here. We also drilled into the top of Turanganui Knoll, which is one of the seamounts, because as we've talked about before, there's, clearly the seamounts are probably also juxtaposed against the plate interface. And so it's very important to get at those properties. So this is just showing some lithologic logs and other physical properties and of that blue interval here. This is the target interval where the décollement's forming. And we really have a pretty amazing diversity of lithologies going on here with quite varying properties. Sort of in the top of this blue zone, we encountered quite a lot of carbonates. And then beneath that, a large package of volcaniclastic sediments. A lot of those have been altered heavily to smectite clays based on XRD work done by Mike Underwood and others. And you can see some very large changes in porosity of these materials in this zone, and also P wave velocities. So there's probably a lot of, variations in the frictional behaviors of these materials, and so a lot of rheological and lithological heterogeneity going on that we think is probably very important in promoting these shallow slow slip events to happen. Okay, so this is just a few recent results on from some of the rock deformation experiments that have been done on these North Hikurangi slow slip event protolith rocks. And this is a compilation and a lot of the data as well as from Srisharan Sridharan, recently finished PhD student from Penn State. And what his work is showing is that as you increase your upstep velocities, you actually change your A minus B and also your D sub C. You push your A minus B more into that velocity strengthening region with these higher velocities. And this is really suggesting that as you start to have higher slip velocities, then you start to become more velocity strengthening, which will sort of arrest kind of potential for seismic sort of slip. So this may be a really important mechanism for keeping the slow slip slow. And this has been suggested by others from rock deformation experiments on other materials from elsewhere, and also from numerical modeling studies. Okay, so then I want to talk a bit about some really there's been quite a few people doing a lot of work trying to understand the impact of seamounts on the subduction margin properties. In particular, Tian Sun and Susan Ellis and Damian Safer did some really interesting numerical modeling work that was published last year. And they're showing from the predictions of their numerical models above the seamount, where you get a lot of fracturing of the overlying plate, you get essentially under consolidation or higher porosity than would be expected there, and higher porosity relative to the surrounding rocks in the overlying plate. And then in front of the seamount on the landward side, you get an over-consolidation or lower porosity. And this over-consolidated area, predicted over-consolidated area, is also where we see the tremor from the Hobbits experiment. So this is showing some really interesting predictions that then ultimately, I hope in the next few years, because there's been seismic lines collected through this area of seamount subduction, that some more analysis will be done to start really pulling out some of the physical properties of the overlying plate and the plate interface from the seismic imaging data to really test some of these models of the impact of seamounts on the subduction margin properties. And this is just showing a few tantalizing examples of this. At the top is a VP model and also anisotropy from Ryuta Arai, a paper that was published, I think it was last year. I highly recommend looking at it. It's a pretty interesting paper in this seamount subduction area. And then also some work that Andrew Gaze has been doing on a nearby seismic line from the Shire experiment. So I kind of want to say, watch this space. I think there's going to be some interesting observations coming out. There's also been some interesting observations in terms of anisotropy, both from shear wave splitting from the Hobbits OBS deployment, and then also P-wave anisotropy from the work that Ryuta Arai's been doing. This Ryuta Arai's work has been based on the 3D seismic data set, and where there was also ocean bottom seismometers deployed during that 3D seismic experiment. But you can see, it's a little busy to look at, but here's that subducted seamount here in red, S2. And you can see above the subducted seamount from the shear wave splitting, you're getting mostly margin normal fast directions. And then behind that seamount, landward of that, it rotates around to margin parallel. You see a similar thing in the Arai et al. P-wave anisotropy. You see mostly margin normal, and then you rotating around to margin parallel. So there could be some changes in anisotropy. And if the anisotropy is somehow related to stress orientations in response to the seamount subduction, although we also need to be considering things like fault foliation and clay mineral alignments and so forth as well, or those could be in response to the seamount subduction as well. So I think there's going to be some really interesting things to kind of tease apart what these things mean in terms of seamounts. Okay. So this, for the shallow slow slip events, some of the advances before I get into the last several minutes of the talk, the seafloor geodetic studies are suggesting slow slip occurrence, very close to the trench, within at least 2 kilometers of the seafloor. We'll probably have a lot more insight on that once we get the Cork Observatory data next month. These subducting seamounts are having a lot of influence on the locations of the tremor, potentially the slow slip, possibly properties of the upper plate, and anisotropy at the subduction zone. The highest slow slip region does appear to coincide with this high amplitude reflective zone, which may be underplated fluid rich subducted sediment, or it may not be. I think that's still open to interpretation. And then, the fault zone, we think the slow slip in this region is really going to be heavily influenced by heterogeneities at multiple scales, from larger scale geometric heterogeneities of these seamounts to sort of smaller scale lithological heterogeneities. And then the rock deformation experiments are also suggesting some slip rate dependent changes in frictional properties may favor these shallow episodic slow slip events. And finally, the properties of the overriding plate, I think, are very important in influencing whether or not you have dynamic triggering of shallow slow slip by more distant earthquakes. Oh, and one more point, shallow slow slip regions, I think, are also capable of hosting seismic slip. Okay, so I want to talk in the last several slides about exploiting these along strike variations that I mentioned earlier, from this deeply locked plate boundary in the south to the mostly creeping one in the north. And what can we get out of that in terms of trying to pull out what are the physical controls on these different styles of megathrust slip behavior. So a big one that you guys are probably already thinking about is, we do see a big change from quite a rough incoming plate here, and we probably have a very heterogeneous plate boundary fault in this northern area where we have mostly creeping and shallow slow slip versus this sort of smoother, more sediment blanketed plate boundary in the south. And Kellen Wang and Sue Billick have had quite a few papers over the years where they've proposed that this sort of smooth versus rough plate interface probably influences locking versus creeping at subduction zones. And I think this is relatively consistent with what we see at the Hikurangi subduction zone. And they propose that this would be the case because where you have these seamounts and things coming in, you'd have very heterogeneous stress on the plate interface, and that would tend to promote accommodation of the plate motion and smaller to moderate magnitude earthquakes and possibly aseismic slip events versus a area where you have a relatively uniform plate interface where you can lock up over a really big area with a relatively uniform sort of stress accumulation for a very long time and then slip in big earthquakes. So I think this is probably a big player in explaining what we see at the Hikurangi margin. But I think there's also, I don't think it explains everything because we don't see a really abrupt, it's a more gradational change in terms of the roughness of the incoming plate. It's not abrupt. So I think we also need to be thinking about some other factors as well. One of the other striking things that we see here in terms of changes in properties that coincide with this shift in deep locking to mostly creeping are properties of the upper plate, particularly in terms of the seismic properties. This is just showing the figure on the left. We have generally lower P wave velocities in the north in the creeping area and higher velocities in the upper plate in the south. Then also similarly, we've got high VPVS in the north. This is on this figure on the right from Don Eberhard Phillips and Martin Rainers, and lower VPVS ratios in the south. And this may be telling us something about either fluid pressures in the upper plate or the degree of interconnected fluids and permeability. And we really need to be thinking about how that may play into this sort of variations in slip behavior that we observe. I also mentioned earlier the taper angle of the offshore wedge. There is a steep taper angle in the creeping area and a shallow taper angle in the mostly locked area. So there may be something about the properties of the wedge or the friction on the plate boundary that relate to the locking versus creeping that's manifested in the wedge morphology. So this is just showing a P wave velocity inversion from Dan Bassett, and this is from the Shire experiment. This is from a strike line. Basically, I'll show you. This is this line right here, where they had ocean bottom seismometers deployed during the active source shooting. And this on the left is in the locked area, and on the right is in the creeping area. And Dan sees a very sharp change in the VP in the upper plate. Above the creeping area, VP is generally lower, and above the locked area, it's generally higher. Is this somehow suggesting that the properties of the upper plate may somehow influence the ability of the plate of the plate boundary to lock up and the surrounding crust to accrue elastic strain for long periods of time, or is something else entirely at play here? For example, are these seamounts influencing the fracturing and so forth in the upper plate? So I think that's something we need to tease out, a kind of cause and effect for some of these observations. And then this is a few highlights from some controlled source electromagnetic experiments that Carrie Keith, Samar Naif, and Christine Chesley did offshore the East Coast. This is a really beautiful data set. I'm really impressed with what they've done here. They're measuring basically changes in conductivity structure of the offshore subduction zone. And the upshot that I want to point out with this figure from Christine is that in the northern part of the margin, in this shallow slow slip area where you also have a lot of seamounts coming in, you've got a very heterogeneous complex porosity structure that's developed. Is this somehow in response to these seamounts subducting, potentially fracturing up the upper plate, or is something else going on? But I'm really excited to see some of the work by Christine and her colleagues hopefully coming out sometime soon. And I couldn't resist showing, this is the anisotropy, the P wave anisotropy from Ryuta Arai, essentially along the same transect. And you see very complex anisotropy structure appears to be coinciding with the faults in this area. So I think there's going to be some really interesting things coming out with integrating some of these seismic imaging data sets and the controlled source EM work. Okay, and I've got to give a shout out to my colleague Deepka Heise at GNS, because these guys have done, over the last 10 years, have been basically emptying their brains out, collecting about 470 magnetotelluric measurements in the eastern part of the North Island and the forearc of the subduction zone. I think this is probably one of the biggest MT data sets of any subduction zone in the world. And they've been able to really pin down the conductivity structure from the MT. And they've observed a lot of interesting things. One of the more interesting things that I want to highlight here in terms of megathrust behaviors in the south, you can see this cross section here on the lower left. This is from the south, and where the plate interface is locked, you have a more resistive structure. You don't have high conductivity on the plate interface. Where you go north in the areas of creep, you do have a little more conductivity on the plate interface. And this may be telling us something about the degree of interconnected fluids, or possibly even fluid pressure and the currents of creeping versus locking. Okay, so to recap, hopefully this is basically the end. I have a few minutes for questions, but so this is the overall picture of currently what we're seeing in terms of changes in physical properties along this change from deep locking in the south to mostly creeping in the north. We see big changes in seismic properties, low VPVS in the south, higher VP and QP in the forearc in the south, a smaller wedge taper in the south, thick incoming sediment, smoother plate, low conductivity plate interface. And also, I didn't get a chance to get into the fluids story, but there's some really interesting things in terms of the volumes of fluids emerging at the surface and also the geochemistry of those fluids. But there's smaller volumes of fluids emerging at seeps and springs in the surface in the south. In the north, the mostly creeping, we have high VPVS in the forearc, low VP and QP in the forearc, a larger, steeper wedge taper, thin sediments, rough plate, very heterogeneous conductivity structure, and large volumes of fluids emerging in the onshore. And so I think we're sort of on the cusp of getting at what's controlling this big change in megathrust slip behavior that we see here. However, I want to put a big cautionary note out there is I think the challenge lies in distinguishing which are the most important factors and why, and really trying to resolve some of the feedbacks between these things. I think it's very tempting to ascribe these changes to one single factor. However, subduction zones are complex systems and complex beasts. And we can only see bits and pieces of it. And so putting the whole picture together is really the challenge. And this cartoon from Susan Ellis, which I love this cartoon, is showing a bunch of blindfolded scientists basically looking at different parts of an elephant, trying to figure out what it is. The guy up here on top, he thinks it's all about the upper plate. Down here, these guys are all about the input sediment properties. We need to be putting this all together and developing a kind of holistic picture that ties all the observations together. Okay, emerging patterns, the things that I do think probably are important, clearly multi-scale heterogeneity, particularly in terms of these shallow, slow slip and creep in the northern part of the margin. Fluids are likely playing some kind of role. We need to tease that out, although there's certainly some uncertainties in the interpretation of a lot of the seismic things like VPVS in terms of what that means in terms of fluid pressure. So we need to get a more refined understanding of that. I think the upper plate properties and the structure is important. We do see big changes in concert with the coupling and the slip behavior. And then, as I mentioned before, we've got to treat this as a total system and with feedbacks and not just focus on one or two parameters to really figure this out. So there's been, as I mentioned earlier, heaps of people involved in this. This has been all of this work that I've talked about has really been a truly international effort, involving people from, the US, Japan, New Zealand, the UK, Europe, and other places. And I just want to acknowledge a lot of those and also funding agencies there. So, and then I want to give just final perspective from the Southern Hemisphere. It's probably a very sunny perspective because it's the summer here and we don't have COVID. But I just want to say that from this perspective down under, programs like GeoPrism's SZ4D and IODP have been really, really instrumental in fostering a vibrant, really collaborative global community of subduction scientists. And also from the New Zealand perspective, the investment and interest generated by these types of programs really tangibly spurs on increased investment in subduction science from governments in other countries like New Zealand, which really helps to greatly magnify outcomes. So I'm really looking forward to see SZ4D hopefully take off soon and continue to kind of contribute these really important aspects. So thank you.
Great, thank you for that talk, Laura. I'm Melody French from Rice University, and I'm going to be moderating the Q&A. So as Harold typed in, any of you with questions, you can just type them into the chat and then I'll read them out. So there's actually one question that came in pretty early in the talk from David Lumley. Can you share any thoughts about time-lapse velocity changes in terms of percentages that might be occurring due to stress strain changes before and after earthquakes?
I can comment on that more in terms of seismic velocity changes during slow slip events, because we're actually seeing some of that during the Hobbits experiment. A student at Victoria University has been working on this, and she sees, I think it was a few percent change in, I think it was in VS. I should remember this because I read the paper a couple of weeks ago. But yeah, so we are seeing some indication of seismic velocity changes in response to the slow slip events. And whether, I think the big question is whether those changes are occurring in response to the crustal strain, if that's changing the seismic velocities, which I think certainly is going to play a big factor. And then also if there's any changes in fluid migration and so forth that, like, say, Emily Warren Smith has suggested for the 2014 slow slip event from the Hobbits experiment. So, but yeah, I can't necessarily comment on that from earthquakes because I haven't looked at that, but there may be others in the audience who have. So.
The second question is also from David Lumley, and it's the Bassett strike line result of lower VP in SEDS in creeping area versus higher VP SEDS in locked area may indicate much higher pore pressure in creeping SEDS. Do you have any thoughts on that?
Yeah, so that's where we need to get at the question of what do these VP changes mean? I think a knee-jerk reaction is to say it's pore pressure. It could be more interconnected fluid. I mean, more interconnected fluids. You know, I think we really need to get at what that VP change means. So it could mean higher pore pressure in the upper plate in the north than the south, or it could mean something else entirely. And I think one of the keys to getting at what that means is bringing these observations together rather than just looking at VP in isolation. I think there's some folks involved in these experiments that are planning to do some full waveform inversion on the seismic data, which will help to get a better handle on the seismic properties. And also integration with the controlled source EM data sets as well will help a lot with this. And then one of the other things I want to point out, what Dan thinks the source of this change is actually something is more related to the sort of intrinsic structure of the forearc there, that in the south, there may be older terrains involved in that forearc and closer to the trench there compared to further north. And that, you know, this may be kind of a consequence of the history and the evolution of the sort of inner forearc in this part of the subduction zone. So I think these are some of the challenges going forward, is figuring out exactly what this means.
Kellen Wang asks, have shallow VLFEs been detected at North Hikurangi? They are abundant at Kyushu and are also in parts of Nankai and Japan Trench.
Yeah, that's a challenge. And for the 2019 slow slip event, we had OBSs out. Kimi Mochizuki and let's see, I guess I'll just leave it on this one. It's probably fine. Kimi Mochizuki and Yusuke Yamashita, who Yamashita-san's the one who's identified the ones off Kyushu. They've been having a really hard time identifying VLFEs out here. They've seen a lot of tremor in the 2019 event, actually way more tremor in 2019 than we saw in 2014. So that's interesting, but they're having a very difficult time teasing out the VLFEs. So that's, you know, maybe they'll be able to drill into that data and find some, but that's also a curious, interesting contrast, because you would think that this shallow slow slip area at Northern Hikurangi should be similar to Kyushu, and there's a lot of commonalities between the thermal regime and the roughness of the incoming plate and so forth that you would expect to see similar types of things like these VLFEs they see there, but we haven't clearly seen that yet. So, yeah.
Thank you. Okay, so we're at our 2 o'clock hour, but we're going to take the last, if you have time, maybe the last few questions that came in.
Yeah.
So how much are these, whoa, sorry, this keeps every time changes my screen. How much are these new discoveries changing estimates of the seismic hazard for the region?
Yeah, this is a key thing we're actually dealing with right now because we're in the middle of a revision of the National Seismic Hazard Model, and there's been a lot of effort for the new version of the seismic hazard model that's being put into really incorporating what we've learned about the Hikurangi subduction zone for the Hikurangi part of the source model for the seismic hazard model. So we're bringing in a lot more detail some of the information on slip deficit rates or moment accumulation rates that we can infer from the geodetic coupling, but we're also trying to marry that with some of the paleoseismic work. For example, I mentioned the paleoseismic evidence for rupture along the Hawke's Bay coastline here in this slow slip source area, which currently appears to be mostly creeping. So we can't so I think we need to bring these things together and, not have the sort of northern central part of the margin, mostly creeping with little hazard. I think we need to actually bring in source models that consider the possibility for seismic rupture there. And there's also been a lot of effort in the paleoseismology to really get at the recurrence of earthquakes in the southern Hikurangi subduction zone. And they've been really only in the last couple of years have refined their understanding of the recurrence of past events in the southern part of the subduction zone as well. So this is currently being implemented now. And then I can see in future versions of the hazard model, some of the new findings that'll be coming on board in the next few years will also start being integrated into that. And slow slip, Emily mentioned before, perspectives, from in terms of, just more societal kind of, government concerns and stuff. We had the slow slip event that was triggered following the Kaikota earthquake. This caused quite a lot of concern about potential for increased hazard of either a large earthquake on the southern Hikurangi subduction zone or elsewhere in the central part of New Zealand. And the government took that very seriously, and we spent a lot of time giving them advice and sort of information that could then go forward to inform policy. So New Zealand, we're quite lucky because it's a small country. It's easier to talk to government officials about, kind of more up-to-date kind of understanding that we're gaining from these studies on the Hikurangi subduction zone and also other faults throughout New Zealand. So
just going to go with one more question. I think you answered the last one as well in that answer. So if I remember my geography from the North Island correctly, it seems like the active volcanism on the North Island is also north of that transition. Do I have that right?
Yes. So we've got this area, the Taupo volcanic zone, and this is our main volcanic arc area. And so that's well west of where these, potentially seismogenic processes are happening on the plate interface. However, the Taupo volcanic zone also coincides with extension. It's basically intra-arc extension, rates of about a centimeter a year or so. And I didn't talk about this change before, but there is the transition from extension in the back arc to transpression in the forearc occurs right about here, about where the lock to creeping transition occurs. So one of the other factors that I think we really need to think about is the influence of upper plate stress state on some of these things that we're observing, particularly on the upper plate seismic velocity changes, but also can that create a situation that somehow influences the slip behavior on the megathrust? And we've got a couple of papers that have put out some ideas on that potential interaction as well. So that's another one of these factors to consider. So
I actually missed one question, so this will be the last one.
Oh, no problem. I don't mind. I went on way too long anyway.
There are lots of questions. So is there any evidence of any large earthquakes related to the seamount subduction in the North HSC?
Yeah, so The ones that I mentioned before were the 2 magnitude 7 earthquakes. Those are the largest earthquakes in this northern part where the seamounts are subducting that we've seen in the historical record. New Zealand's got a very short historical record, about 150 years or so written historical record. But the paleoseismologists have been looking along this coastline for evidence of past subduction earthquakes in the northern part. There's not clear, obvious evidence there. If those have happened in the past, maybe that evidence isn't preserved, or maybe they just haven't happened in the past. But that's a big unknown, is whether or not you can get, magnitude 8s kind of cutting through this region in the north. We think you can in the central part based on the paleoseismic data in Hawke's Bay, but we really don't know the answer to that in the northern part, beyond the sort of magnitude 7 tsunami earthquakes that we've seen up there.
Great, thank you. It was really nice to have this sort of summary of all of the work going on in Hikurangi.
Great, thanks for listening.